Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is solve problems in fluid mechanics and hydraulics, problems 19 to 24. Uh, the set of problems here are given in quiz number 2. Problem 19. Water having a bulk modulus of elasticity of 2.2 gigapascals has volume of 1 liter and is compressed at a pressure of 450 kilopascals. So determine the resulting volume in cubic centimeters. So for the solution, we have to write the formula for bulk modulus of elasticity, which is equal to negative of delta P over quantity delta V over V, where V is the initial volume, which is 1 liter, and 1 liter is 1000 cubic centimeters or 1000 cc. It is also 1 liter is also 1000 milliliter. So here's the given formula. Delta P is 450 kilopascals. Then initial volume is 1000 cc or 1 liter. And E sub B is 2.2 gigapascals. Substitute into the formula 2.2 times 10 to the 6 kilopascals. That's gigapascal, so the pressure is in kilopascals. So we should express bulk modulus of elasticity to kilopascals so that uh, the result will be consistent. Delta V will be in cubic centimeter. So solving for delta V is negative 0.2045 cubic centimeter. Then delta V is final volume minus initial volume, where the initial volume is 1 liter or 1000 cc. So substituting, volume final minus 1000 equals negative 0.2045. From here, we can solve the resulting volume, which is equal to 999.7955 cc. So for this problem, supposedly, I'm going to report the answer to 4 significant figures, but this is crucial because the uh, resulting volume is being asked. So let's just leave the answer in that manner. But if this force or pressure, then you can express the answer to 4 significant figures. Problem 20. Oil having a mass of 825 grams and a volume of 1025 milliliter is compressed such that the resulting volume is reduced to 1024.75 milliliter. If the pressure applied is 600 kilopascals, determine its bulk modulus in gigapascals. So let's define bulk modulus of elasticity here as the change in pressure over the relative change in density, where the relative change in density is final density over final density minus initial density, and density is mass, which remains constant, over volume. So E sub B, delta P over delta density over density, it is positive because the change in density is a positive one. The density increases when the given mass of substance, such as oil here, is compressed. So delta change in density is final density minus initial density, and density is mass over volume. So this is 820, final density is 825 over 1024.75 minus 825 over 1025. And the resulting change in density is in grams per milliliter or gram per cc. So change in density is 1.9636 times 10 to the negative 4 gram per cubic centimeter. Then initial density rho is 825 over 1025. So substitute into the formula. bulk modulus is equal to 600,000 pascals over 1.9636 times 10 to the negative 4 gram per cubic centimeter over 825 over 1025 milliliter or cc. So that is consistent. E sub B therefore is equal to 2.459 times 10 to the 9 pascals or 2.459 gigapascals. Problem 21. Determine the hydrostatic force on one side of a rectangular gate 2 meters wide and 6 meters high, as well as the vertical distance of its line of action of intersection with the plane of the gate from the liquid surface for the following cases. Part A, the liquid is water and the top edge of the gate is flush with the water surface and the plane of the gate is vertical. Then part B, the water surface in part A is subjected to a pressure of 20 kilopascals. Part C, the water surface is 2 meters above the top edge of the inclined gate. The plane of the gate is inclined 60 degrees to the horizontal, and the water surface is subjected to a suction pressure of 0.8 meter of molasses with specific gravity 1.5. So for the solution, first solution here, I'll consider force to be equal to volume of pressure diagram and the value of H sub Cp based on the pressure diagram, which is triangular, so that we can solve H sub Cp directly and the hydrostatic force F by the volume. So the center pressure is here, the point where the resultant force acts as shown. So this is the pressure diagram. The pressure here is pressure at the top, which is 0, plus specific weight of water times 6. The plane of the gate is vertical in part A. So this is 9.81, specific weight of water times 6, the intensity of pressure here. And therefore, that's the force F which passes through center of pressure. Since this is triangular distribution, F is computed as volume of pressure diagram. And this is 8 sub Cp, which is 2/3 of 6, so it is known beforehand for meters. So F is volume, and the volume is area of this triangular pressure diagram times width perpendicular to the board, or to the screen, which is 2 meters. So volume is 1/2 of 9.81 times 6 base times height 6 times width perpendicular to the board 2. So 1/2 base 9.81 times 6, that's the base. The height is 6 and the width perpendicular to the board is 2. From there, we can solve F equals 353.2 kilonewtons. Then H sub Cp is 2/3 of 6 directly, and 2/3 of 6 is 4 meters. Then for the second part, we can use specific weight of water, barred H, or H sub G area as formula for F, because we only have one liquid and the surface of water at the top is exposed to the free atmosphere or zero gauge pressure. So substitute where Hg is 1/2 of 6, 3 meters. This is the centroid, and that's Hg, which is 3 meters. And let's call this E, which is expected to be 1. So that's H sub Cp, and this is E sub V. So substitute F is 9.81 times 3 times area, 2 times 6, the area of the plane area of the gate, 2 by 6, or 12. So F is 353.2 kilonewtons, just like this. Then we need to solve E sub V, which is equal to height of rectangle square divided by 12 Hg. So height of rectangle square over quantity 12 times Hg. Hg is 3. Height of rectangle is 6. So 6 square over 12 times 3. And that is equal to 1 meter. So that's why H sub Cp is 3 meters plus E sub V, 3 plus 1 is 4 meters. Then let's proceed to part B. The water surface in part A is subjected to a pressure of 20 kilopascals. So let's use the same figure and let's mark this as point 1. The pressure is P1, which is 20 kilopascals. We can no longer apply this formula unless we convert P1 into equivalent depth of water. We can do that. but I'll use pressure at the centroid times area instead. So PG times area, where P sub G is equal to P1 plus specific weight of water times 3 to reach this point G here. So F is 20 plus 9.81 times 3 times area 2 times 6, where 20 plus 9.81 times 3 is the pressure at the centroid. 20 at 1, then we go down by 3 meters, and the liquid is water, so 9.81 times 3. That's the pressure at G, at the centroid of the area of the gate, then area 2 by 6. So F is 593.2 kilonewtons. Then for HG, we equate 20 plus 9.81 times 3 to the pressure at the centroid, which is specific weight of water because it is water that is in contact with the gate, times Hg. So P sub G equals gamma of water times Hg. P sub G is 20 plus 9.81 times 3, then equals 9.81 times Hg. From there, we can solve Hg, which is equal to 5.039 meters. And you cannot see it here unless you convert this pressure 1 into pressure head. So it will extend a little, 20 divided by 9.81, and that 20 divided by 9.81 plus 3 meters will give us 5.039 meters. So E sub V is equal to 6 square over 12 times 5.039, so 0.5954 meters. So H sub Cp is 3 plus E sub V, 3 plus 0.5954 to 4 significant figures, so H sub Cp is 3.595 meters. Then for part C, the gate is now inclined and the water surface is 2 meters above the top edge and with suction pressure on top. So this is the figure. This is the center of pressure where F acts, and this is 8 sub Cp. That's 60 degrees, inclined 60 degrees. This is the centroid of the gate, and that's 2 meters. Then P1 is subjected to a suction pressure or negative pressure of 0.8 meter of molasses. So computing for P1, and let's call that E, the distance between G and center of pressure along the plane of the gate. So P1 is 1.5 times 9.81 times negative 0.8 meter of molasses. So P sub 1 is negative 11.772 kilopascals. And we use F equals pressure at G times area, where the pressure at G is P1. Then we go down plus 9.81 times 2 plus 3 sine of 60 degrees. So P sub G is negative 11.772 P1 plus 9.81 quantity times 2 plus the vertical distance from G to this point is 3 meters, half of 6, that's G. 3 meters sine of 60. So P sub G is equal to 33.335 kilopascals. Then we equate that to gamma of water Hg to solve for Hg. So H sub G is 3.398 meters. Then we can now solve E sub V. The formula is varied. We can solve E rather. The formula is varied by multiplying sine of theta, where theta is 60 degrees. And E is not the vertical distance between G and Cp, but rather the distance along the plane of the gate. So F is Pg times area, 33.335 pressure at centroid, then area 2 by 6, so F is 400.0 kilonewtons. Then E is equal to height of rectangle square sine of 60 over 12 times Hg, where Hg is 3.398. So E is 0.7646 meters. Therefore, H sub Cp is equal to 2 plus this 2 here plus 3, quantity 3 plus E sine of 60. 3 plus E sine of 60, this vertical distance, additional. So 8 sub CP is equal to 5.260 meters. So that's it for this problem. Problem 22. Each of the three gates has a constant width 2.4 meters perpendicular to the paper or screen. Calculate the force P required to maintain each gate in the position shown. Consider the liquid as water. B is 1.8 meters, H 2.7 meters, and neglect the weight of the gate in each part. If the weight of the gate in parts A and C were considered, what would be the value of P? The gate is made of steel of specific gravity 7.86 and 25 mm thick. So here are the given parts, figures. So for part A, I'll solve this into two ways. One by solving F, which is perpendicular to the inclined phase, and the second one based on the pressure distribution and the weight of water enclosed by the gate itself and the water surface, as well as there's vertical line through A. So for solution 1, this length is square root of B square plus H square. Square root of 1.8 square plus 2.7 square is 3.245 meters. So that's why if F is perpendicular to the plane, because the pressure at the top is 0 and the pressure distribution is triangular, then this is 1/3 of 3.245. The distance of F from A is 1/3 of 3.245 meters. So F is equal to specific weight barred H area. Specific weight HG, I denote barred H as HG here. Distance to centroid from the water surface exposed to 0 pressure. Then area of the gate, which is this length of gate times width perpendicular to the board, which is 2.4. So the area of the gate is 3.245 meters times 2.4. So substitute F is 9.81, then 2.7 over 2, H over 2, barred H. Area 2.4 times 3.245. So F is 103.14 kilonewtons. Then summation of moments about A equals 0. P times H, P times 2.7 equals F times 3.243 over 3. So 103.14 times 3.245 over 3 equals P times 2.7. From there, we can solve for P. P is equal to 41.32 kilonewtons. As another way, use pressure diagram, which is triangular, and intensity of pressure at the bottom is 9.81 times H. So that's 9.81 times H. Then FH is located 1/3, because the pressure distribution is triangular, 1/3 of H. So this is H over 3. And FH is volume of this pressure diagram. 1/2 of area of the triangle, 1/2 9.81 H times perpendicular to the board 2.4. And we have weight 1, weight of water, and its distance is 1/3 of B from this vertical line or y-axis. So FH is volume, and it is 1/2 of 9.81 times H times 2.4. So that's the volume. Area 1/2 9.81 H times H, that's the area of the triangle. Then width perpendicular to the board 2.4, that makes it volume. So it is equal to 1/2 of 9.81 times 2.7 square. H is 2.7 times 2.4, so it is 85.818 kilonewtons. Then weight 1 is equal to 9.81 times volume, 1/2 of B times H times width perpendicular to the board 2.7. So 9.81, 1/2 of 1.8 B, height 2.4, width perpendicular to the board 2.4. So weight 1 is 57.212 kilonewtons. Then summation of moments about A equals 0. P times 2.7 equals FH 85.818 times 2.7 over 3, H over 3, plus W1, which is 57.212 times B over 3 or 1.8 over 3. Solving for P, P is 41.32 kilonewtons, of course, by another method. Then if the weight of the gate is considered, so we'll just compute for P and call that P prime, considering the weight of the gate. The weight of the gate is specific weight of steel times volume of the gate, which is 2.4 times 3.245 times 0.025 thickness. Volume is area of this rectangular gate, and the area is 2.4 perpendicular to the screen times length, which is 3.245 meters, times thickness 0.025. So weight of gate is 15.013 kilonewtons. Then let's apply that, and the distance of that weight from the vertical line through A is B over 2 also. So that summation moment about A equals 0. So P prime times 2.7 equals 85.818 times 2.7 over 3 plus 57.212 times 1 over 3 plus weight of gate 15.013 times 1.8 over 2. Solving for P prime, considering the weight of the gate, 46.32 kilonewtons. So let's proceed to the next figure. We just solved for P here because the weight of the gate is not considered, but if it is considered, then it is to be located by arc length formula and centroid of arc length. So it should be not so challenging if you can remember the arc length formula and apply centroidal coordinates by, or derive the centroidal coordinates of this parabolic arc by Varignon's theorem or by integral calculus first moment of mass principle. So since the tangent at A is inclined, obviously, then as shown, and the tangent at B is vertical, or if you flip or rotate the figure, the tangent at B is horizontal. Therefore, this is the location of the vertex, and it is open to the left parabola. So therefore, the centroid is, this is 2/5, because from here to centroid is 3/5 of B, so 2/5 of B for the weight of water inside this parabolic arc. So this is the pressure distribution. This is still 9.81 times H. FH is the same as in part 1 because the dimension is the same and the condition is the same. This is the projected area. So that's H over 3. Then we have weight 2, and this distance is 2/5 of B. So you must know the location of the centroid of parabola. Again, the vertex is here. And therefore, our weight sub 2 is 9.81 times volume, and volume is area of parabola, which is 2/3 base times height, then width perpendicular to the board 2.4. Area of parabola 2/3 BH, 2/3 base times height, and width perpendicular to the board 2.4. And this is the specific weight of water, so specific weight of water times volume, remember. So 9.81 times 2/3 base times height times 2.4, that is 76.283 kilonewtons. Then summation moment A equals 0, P times 2.7 equals 85.818 times 2.7 over 3 plus 76.283 times 2/5 of 1.8. 2/5 of 1.8. Solving for P, P is equal to 48.95 kilonewtons. Then for part C, here's the given figure, and therefore FH is still the same as the preceding cases. 9.81 H, this is H over 3. Then we have weight of water inside this rectangular figure, and this is B over 2. And that's it for the first part, because in the second part we have to consider the weight of the gate. So weight 3 is 9.81 times volume. Volume is BH times perpendicular to the board 2.4. So 9.81 times 1.8 times 2.7 times 2.4. Weight 3 is equal to 114.424 kilonewtons. Then summation of moment about A equals 0. P times 2.7 equals 85.818 times 2.7 over 3 plus 114.424 times 1.8 over 2. B over 2. So P is equal to 66.75 kilonewtons. Then for the second part, considering the weight of the gate, so let's divide this into two parts. So take note that B is from vertical line through A to this inner vertical edge. So since the thickness is considered, then the moment arm for the weight in this part here would be added half of the thickness. So call this WG1. The distance from A is B over 2, and call that WG2. Its distance from A is B, which is 1.8 plus half of the thickness, 0.025 over 2. So it is 1.8125 meters. So WG1 is 7.86 times 9.81. Volume is B 1.8, perpendicular to the board 2.4, thickness of gate 0.025. So that's the volume of this horizontal portion of the gate, and that is 8.328 kilonewtons. Weight G2 is equal to 7.86, 9.81 times H 2.7, perpendicular to the board 2.4, and thickness 0.025. So therefore it is 12.491 kilonewtons. Then summation moment about A equals 0. So P prime times 2.7 equals FH 85.818 times 2.7 over 3 plus W3, which is 114.424 times B over 2 plus WG1 8.328 times 1.8 over 2 plus WG2 12.491 times 1.8125. So solving for P prime is equal to 77.91 kilonewtons. So that's it for this problem. Problem 23, the figure shows a trapezoidal gate on an end panel. Determine the moment of the hydrostatic force, part A about AB and part B about BC. So here is the given figure, and we have a gate which is trapezoidal, so composite area. We have to divide this into two parts, rectangular and triangular, as shown. So this is the dividing line. So the rectangular gate is 1.5 width, 4.5 meters high, and for the triangular gate it is 2.4 minus 1.5, so 0.9 meter here, base height 4.5. So for the location of the centroid of the rectangular gate, it is here. Then this is the G of rectangle, G sub R. Then the location of the force is below, and that is CPR, center of pressure of rectangular area. It is where FR acts, and the distance between them along the plane of the gate is denoted by E sub R as shown. Then for the triangular part, this is the centroid, so that's G sub triangle. Then the center of pressure is below, call that CP triangle, and this is where F triangle acts, and the distance between GT and CPT is E sub T as indicated in the figure. So this is also CPR, and this is CP triangle where FT acts. And if the length of the line through the center of pressure of the triangle is x1, then the force Ft acts at the midpoint of that x1. So take note of that by principle. So this distance is 1.8, then distance from A to G, centroid of rectangle is half of 4.5, so 2.25. So the vertical distance is 1.8 plus 2.25. This is 2.25 hypotenuse sine of 50. So 1.8 plus 2.25 sine of 50 degrees is equal to 3.5236 meters, so that we can compute directly the pressure at the centroid, because I'll use the formula for computing these forces, hydrostatic forces, I'll use the formula pressure at G times area of the figure. Then for the distance of the centroid of the triangular part to the oil surface, this is 1.8. So the distance from A to G of triangle is 2/3 of 4.5. 2/3 of 4.5 is 3. So it is 1.8 plus 3 sine of 50. 1.8 plus 3 sine 50 degrees, that would be 4.0981 meters. So part A, F, R is pressure at GR times area of rectangle. The pressure at GR is 15 plus 0.84 times 9.81 times 3.5236. That's why we computed 3.5236, so that we can compute the pressure at the centroid of rectangle directly. So beginning with the surface, 15 kilopascals, going down, so plus specific weight of oil 0.84 times 9.81. Vertical distance to centroid of rectangle is 3.5236. So pressure at G of rectangle is 44.036 kilopascals, and that should be equated to specific weight of oil times HGR, because HGR is not seen here. So it is equated to 0.84 times 9.81 times HGR, so that we can compute HGR in computing for ER later. So 5.3439 meters of oil. Another way is you convert 15 kilopascals to pressure head of oil. 15 divided by 0.84 times 9.81 and add 3.5236 to get 5.3439 meters of oil. That's the other way of computing HGR. So F of rectangle is equal to 44.036, area of rectangle 1.5 by 4.5. So it is equal to 297.243 kilonewtons. Then for the FT, F sub T is pressure at the centroid of triangle times area of triangle. So the pressure at the centroid of triangle is 15 plus specific weight of oil 0.84 times 9.81 times this vertical distance 4.0981. So GT is 15 plus 0.84 times 9.81 times 4.0981, and that is equal to 48.77 kilopascals, then equated to specific weight of oil times Hg of triangle, because it is the oil that is in contact with the gate. So we use specific weight of oil times HGT. So HGT is equal to 5.9184 meters of oil. So another way of computing HGT, convert 15 into pressure head of oil. 15 divided by 0.84 times 9.81, then add 4.091, you will get 5.9184 meters. So that's the other way of computing HGT. Then compute force due to triangle. E of rectangle, by the way, it's HR square sine theta over 12 HGR, where HR is the height of rectangle, which is 4.5, which is the same height of the triangle also. So 4.5 square sine of 50 degrees over 12 times HCR 5.3439, and therefore E sub R is equal to 0.2419 meters. That is important in computing for the moment about BC later. E of triangle is height of triangle square sine of theta over 18 hg of triangle from original formula, moment of inertia with respect to centroid over area of triangle barred y, where barred y is barred h or h sub g over sine of theta. That's why the formula looks like that. Then after simplification for triangle, because the moment of inertia of triangle is b, height of triangle cube over 36, and area is 1/2 b height of triangle, so that's why it reduces to 1 over 18 like this. So substitute A of triangle is 4.5 square sine of 50 degrees all over 18 times quantity 5.9184 for HGT. So it is equal to 0.1456 meter. So Fx1, by the way, by similar triangles, x1 as to 3, because the distance from A to centroid of triangle is 2/3 of 4.53. Then we add E sub triangle, which is 0.1456, and it is equal to 0.9, which is this, as to 4.5. So solving for x1, x1 is equal to 0.62912 meter, which is important in computing for the moment about AB. So F triangle is pressure at the center of triangle 48.77 times area of triangle 1/2 of 0.9. This is 0.9 base times height 4.5. So F of triangle is equal to 98.759 kilonewtons. Therefore, moment about AB can now be computed. It is FR 297.243 times, because the centroid of triangle is here, center of pressure is here, it is half of 1.5, so moment arm is 0.75. It is direct, the centroid and the center of pressure are aligned on the axis of symmetry. So this distance is 0.75, half of 1.5. While the moment arm of F of triangle, which is acting here, is from AB is 1.5. This is already 1.5 by principle x1 over 2. So the midpoint of this line through center of pressure of triangle, x1 over 2. So moment arm of FT is again 1.5 plus x1 over 2. So plus 98.759 times quantity 1.5 plus x1 0.62912 over 2. So computing for MAB, MAB is equal to 402.1 kilonewton meter. Then moment about BC is equal to F of rectangle, which is 297.243, the distance of CPR from the bottom BC is half of 4.5, 2.25 minus ER, because FR acts here. So that this moment arm or this distance is half of 4.5, because this is rectangle, the centroid is half of 4.5, then minus ER. That's the moment arm of F rectangle. So moment BC is 297.240 times quantity 2.25 minus 0.2419 plus moment of the force due to the triangular area is Ft, since the distance of the centroid of the triangle is 2/3 of 4.5 or 3 meters from A, then its distance from B is 4.5 minus 3, so 1.5. Then minus E of D. So therefore, the moment arm of F triangle is Again, the distance of centroid of triangle to B is 1/3 of 4.5, so 1.5, then minus E of D, so because FT is closer to B. So plus 98.759 times quantity 1.5 minus 0.1456. So MBC is equal to 730.7 kilonewton meter. So that's it for this problem. Problem 24, refer to the figures shown below. Part A, determine the ratio of the hydrostatic force acting on the upper half to that of the hydrostatic force acting on the lower half of the plate that is in contact with the liquid surface on one side for the case where Part A 24A1, H is 0, 24B1, H is X, where X is the edge dimension of the square plate shown. So here is the square plate, and the assumption is the plate is in contact with just one liquid, one side. So call that in general as H. It is 0 in the first part. Then this is the line that divides the area into halves. So area upper and area lower equal, the dimensions XX. Then if this is the centroid of the upper half, then the distance to the liquid surface is HGU. This is the centroid of the lower half, then its distance is HGL, as shown. Then because this is X and this is 45 degrees, this vertical distance from vertex to this line here, dividing line, is X sine 45 as shown. And since this is the centroid of triangle, this is 1/3 of the height, 1/3 of X sine 45. Likewise, this is 1/3 of X sine 45 degrees. So ratio equals gamma, let's call that R equals F upper over F lower. F upper is gamma of liquid, Hg upper, then area, over gamma of liquid, Hg lower times area. Since the liquid is common, we can cancel gamma, and we can also cancel area because the area of the upper half is equal to the area of the lower half. So the ratio reduces to HGU over HGL. And HGU can be read from the figure. It is equal to H plus X sine 45. Then we go up X minus X sine 45 over 3 for HGU, while Hg lower is H plus X sine 45 plus X sine 45 over 3. So H plus X sine 45 degrees minus X sine 45 degrees over 3 for HGU, then over H plus X sine 45 plus X sine 45 degrees over 3 for HGL. For case 1, H is 0, so you just set that to 0, and X sine 45 minus 1/3 of X sine 45 is 2/3 X sine 45, then X sine 45 plus 1/3 X sine 45 is 4/3 X sine 45. So cancel out X sine 45, cancel out 3, ratio is 2 over 4 or 1/2. Then for the second part, we use the same formula. Then H is X this time. So over X plus X sine 45 plus X sine 45 degrees over 3. So substitute, R is X plus 2/3 of X sine 45 degrees over X plus 4/3 of X sine 45. So cancel out X, then compute the ratio using the calculator. R is 0.7574.